Welcome back to our unit on atomic theory. This is the last video for this unit, and we're going to be discussing the periodic table, the shielding effects, and most importantly, periodic trends, or periodicity. Let's go. Alright, you will find a blank page on the back of one of your notes pages, and on that page I want you to draw a rough sketch of a periodic table. We're not looking for anything specific, I just want to show the general sections of the periodic table. Okay, starting from left to right, in group 1, we have the alkali metals. The alkali metals are sodium and potassium. They all have a charge of +1 because they tend to lose 1 electron. In group 2, we have the alkaline earth metals. That would be calcium and magnesium. They all have a charge of +2 because they're likely to lose 2 electrons. And then in the center, we have the transition elements, or the transition metals, known by both names. Then over here underneath the staircase, these are just general metals. And we're not going to forget about the inner transition elements, or the inner transition metals at the bottom. The lanthanide series starts with lanthanum, and the actinide series starts with actinium. So that's the lanthanide and the actinide for the F block. So pretty much everything on the right-hand side of the periodic table, all the way up through that staircase, these are all just metals. Then we have metalloids. Metalloids is the staircase itself. These guys have properties of metals and nonmetals, so they're semiconductors. They'll conduct electricity to a small extent, but not as much as metals do. So the metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and astatine. Alright, then we've got over on the right-hand side, this is the nonmetals. These are all nonmetals. We have group 14, which can have a plus or a -4 charge, so carbon can go either way, although it's usually positive. Group 15 starts to be the negative charges. Group 15 would tend to gain 3 electrons instead of lose. Group 16 would tend to gain 2 electrons instead of lose. Then we have the halogens in group 17, all with a -1 charge because they would gain 1 electron. And finally, the noble gases on the right with no charge because they won't gain electrons or lose electrons. They're very unreactive as a whole group. So pretty much all of the periodic trends that we're going to introduce have to do with the size of the atom and the number of protons in the nucleus. And that can mostly be boiled down to the shielding effect. We had previously talked about the shielding effect in our earlier video. Successive shells are larger than the previous shells, which means shell 2 is larger than shell 1, shell 3 is larger than shell 2, energy level 4 is larger than energy level 3, and so on. The electrons in the successive shells spend more of their time farther from the nucleus, so an electron in energy level 4 will spend more of its time further from the nucleus than an electron in energy level 1. Electrons in successive shells are partly shielded from the attractive forces of the nucleus by the previous shells, so the electrons in row 3 and 2 and 1 will shield the electrons from row 4 from the nucleus. And repulsive forces caused by this shielding effect reduce the effective nuclear charge experienced by the outer electrons. The effective nuclear charge pretty much being how much the outer electrons can feel the protons from the nucleus, from the center of the atom. So effectively what the nuclear charge is, not actually what the nuclear charge is. So the first trend we're going to talk about is atomic size, or atomic radii. That's half the distance between the nucleus of 2 adjacent atoms, or essentially how far 2 atoms are away from each other. This is primarily due to ZEFF, which is the effective nuclear charge and the number of electrons in an atom. So before I get started, I'm going to draw a very miniature periodic table just so we can have an idea of what we're talking about. So as we go across the period from left to right, atom size decreases. In other words, argon is smaller than sodium, even though they're both in the third period. And so that is because within the same energy level, protons are being added, to the nucleus. So electrons are drawn closer to the nucleus. And according to Coulomb's law, this increase in positive charge increases the force of attraction experienced by each electron, thereby decreasing the radius. So as we add more and more and more and more positive charges into the nucleus, and say we have 1 energy level, 2 energy levels, 3 energy levels, the more positive charges we get, the more the electrons on the outermost energy level are being drawn in. The effective nuclear charge is greater. If we go down a group from top to bottom, the atom size increases. So if we went from sodium down to francium, francium would be larger than sodium. And this is because when an energy level is added, the size of the orbital increases. With every layer that's added, the radius increases. Outer electrons experience a greater shielding effect, which means that they have a lower effective nuclear charge. Okay, so according to Coulomb's law, the force of attraction decreases as the distance between the electrons and the protons increase. So if we looked at my picture from earlier and added another ring, say this is the 4s energy level and this is the 3s energy level. The 4s orbital has the exact same shape as the 3s orbital, just a larger diameter or a larger radius. So an electron on the 4s energy level will necessarily be farther from the 3 than the 3s electron would be. Also, even though there are more protons in the nucleus, the shielding effect by the energy levels that are on the inside keep that outer level electron from being able to feel the nucleus as much. So the orbitals themselves are getting larger, but the shielding effect is larger, so the effective nuclear charge is overall smaller. So another periodic trend we've got is ionization energy. Now we had previously discussed ionization energy in a previous video. It is the energy required to remove an electron from a gaseous atom or ion. So we're talking here about fluorine is turning into fluorine plus an electron, taking an electron away from fluorine. Or sodium is turning into sodium plus an electron, taking an electron away from sodium. One of those is going to look a whole lot more normal than the other, and one of those is going to take a whole lot less energy than the other. We're going to discuss that in just a second. So again, let me draw a baby-sized periodic table. Here's my very small one. And so that way we can discuss the trend. As you go across a period, say from sodium to argon again, as you go across, the ionization energy increases. This is because the atomic radius decreases. And more energy is required to move an electron that's closer to the nucleus. So argon has a smaller radius than sodium, so the outermost electron in argon is closer to the nucleus than in sodium. Therefore, it takes more energy to pull that magnet apart. So this would be why this does not look normal. Fluorine should not lose an electron. Fluorine should not turn into fluorine plus, and it takes an incredible amount of energy to do that. But sodium will look normal because sodium will easily lose an electron, and it won't take very much energy for that to happen. As you go down a group, so say from sodium down to francium, the ionization energy decreases because the atomic radius increases. And just the opposite statement as before, less energy is required to remove an electron far from the nucleus. The electrons in francium fill up 7 energy levels. The electrons in sodium only fill up 3 energy levels. So the electron in francium is very far away from the nucleus and won't take very much energy to remove, whereas the electron in sodium is comparatively very close to the nucleus and therefore would take a much more energy to remove. Here's actually a graph of the first ionization energy. That's energy to remove the first electron from an atom. We have hydrogen here somewhere around 1300, helium up to about 23, lithium down to 500. Notice as you go across a period, say from lithium to neon, ionization energy in general increases. And when you jump down a group, say from neon down to sodium, ionization energy decreases. It increases across and it decreases as you go down. So if we went down to the noble gases, from helium down to radon, the ionization energy decreases as we go down the periodic table. And the same thing happens, although it's not as pronounced, for the alkali metals for group 1. So let's look at some of the irregularities that we see in this chart. So I've zoomed in on just the first 3 periods of that previous slide from helium down to argon. And notice that from Be to B, from beryllium to boron, the ionization energy decreases. And again, it happens from nitrogen to oxygen. You'll see it here from magnesium to aluminum, and again from phosphorus to sulfur. So let's talk about why that happens. First, from beryllium to boron, ionization energy decreases because the outermost electron in boron and remember, the ionization energy is the energy to remove the outermost electron. So we're talking about the one the farthest out. Is in a 2p orbital. But if we're looking at beryllium, the outermost electron is in a 2s orbital. Now recall, an electron in a 2s orbital can get closer to the nucleus than an electron in a 2p orbital. Even though they both have the same radius, an electron in an s orbital has greater penetrating power. So it takes more energy to remove an electron that's closer to the nucleus. Now remember, across a period, the ionization energy is going to increase because of the greater nuclear charge. So this effect only happens with beryllium and boron. By the time you get to carbon and nitrogen, the greater nuclear charge will take over and the outermost electrons will be harder to remove again. But just between beryllium and boron, just with that one extra electron, since it's in a 2p orbital, it's a little bit further away from the nucleus and requires a little bit less energy to remove. So now, if we're going to look at the nitrogen-oxygen case, in nitrogen and oxygen, we have oxygen requires just a little bit less energy to remove its outermost electron. So we're going to refer to those orbital filling diagrams that we did in the last video, and this is just the 2p electrons for nitrogen and for oxygen. Now nitrogen is the third over in the p block, which tells me it has 3 p electrons, 1, 2, 3. Recall that those 3 electrons are going to be in 3 separate orbitals, not doubled up, because the electrons, since they have repulsive forces, would rather be further away. But for oxygen, there's 4 p electrons. So after you put the 3 in 3 separate orbitals, one of them is going to be paired up. So the amount of energy it requires to remove an electron from oxygen is a little bit less because there's already a repulsive force between the other electron that's in that same orbital. Whereas for nitrogen, there's not an additional repulsive force from an electron in the same orbital because none of the electrons are in the same orbital. So let me get that written down. 2 electrons in oxygen's 2p orbitals are in the same orbital. Repulsive forces between those two electrons mean that less energy is required to remove one of them. Okay, so then you see that happen again in group 3, that is between magnesium and aluminum, because we're adding an electron to the 2p energy level, and then again from phosphorus to sulfur, because you're adding a paired electron in the 2p orbitals, rather than just single electrons in the 2p orbitals. And you'll see those trends kind of happen as we go all the way through the first ionization energy. So successive ionization energies are the second ionization energy, the third ionization energy, which is the energy required to move the second electron, or the third electron. Each successive ionization energy is greater than the last. The first ionization energy to remove the first electron will be smaller than the second ionization energy, which is the energy to remove the second electron, which will be smaller than the third ionization energy to remove the third electron, and so on and so forth. There is a large jump in ionization energy when removing an electron from a filled energy level or sublevel. So let's look at this chart that we have here. For sodium, it takes 496 kilojoules per mole to remove one electron. So then, if you remove that one electron, it would have 10 electrons just like sodium and have a full second energy level. So if you wanted to remove another one from that sodium, it would require 10 times as much energy, because now you're removing an electron from a filled energy level or filled sublevel. For magnesium, it takes more energy to remove the second electron than the first, because once you've removed the first electron, the next electrons are closer to the nucleus. But then look at how much happens when you try to remove the third electron. Once you try to remove that third electron, you're removing it from a filled energy level or sublevel, and it requires significantly more energy. In this way, you can actually, by looking at the successive ionization energies, determine which element you're looking at. When you see the large jump in ionization energy from 2,000 to 11,000, from 4,000 to 16,000, from 6,000 to 22,000, you can tell that an atom would relatively easily lose, in this case, 5 electrons, but it would require a significant amount of energy to lose 6 electrons. Therefore, this atom must be in group 5 or group 15, and it so happens that it's phosphorus. So then we've got to talk about ion formation. Metals lose electrons to become cations. Remember, cations has that positive sign right there in the word. That's a positively charged ion. So sodium will tend to lose one electron to become Na+. Nonmetals will gain electrons to become anions. And the way we're going to remember that, remember anions are a negative ion. So then fluorine would tend to gain an electron to become fluorine minus. That's the normal way you're going to see fluorine. General oxidation numbers, though many atoms can have other charges. Group 1 is generally +1. Group 2 is going to be +2. Group 13, skipping over the transition metals because there's lots of variations in the transition metals, will be +3. By the time you get to group 14, it's just as easy to gain 4 as it is to lose 4, so +4 or -4. Group 15, it would take less energy to lose 3 than gain 5, so gain 3 than lose 5, so gaining 3 is a -3. Group 16 would prefer to gain 2 because it requires less energy than losing 6. Group 17 would prefer to gain 1 because it requires less energy than gaining 7. And then group 18 tend to be inert. Some of the larger noble gases will form compounds, but most won't. And then we've got just a vocabulary word here for you. Isoelectronic means two atoms that have the same number of electrons and therefore the same electron configuration. So sodium, once it's lost an electron, will have the same electron configuration as neon. Fluorine, once it's gained an electron, will have the same electron configuration as neon. So sodium plus, after it's lost one, is isoelectronic with neon, and also with fluorine minus after it's gained one. So let's talk about ion size. And to do that, Again, I'm going to draw my little periodic table just so we have a way to see things. Cations, or positive ions, are always smaller than the parent atom. So if we're looking at sodium, approximately right here, that will end up being larger than the ion, Na+, or the cation is smaller than the parent atom. Na+ is smaller than Na. That is because when you're removing electrons, the number of protons stays the same, but the number of electrons repelling each other is reduced. Electrons are lost. Protons are not. And so this allows the further out electrons to be pulled closer to the positive nucleus, and the amount of positive charge pulling on each electron increases. So if we think about Coulomb's law, now there's a greater magnitude difference of charge. Additionally, many atoms lose their outermost shell when they lose their valence electrons, and therefore their radius will decrease dramatically. Electrons are lost, protons are not. Outermost shell, or energy level, is removed. So therefore, remaining electrons experience a greater effective nuclear charge than it did originally. So if we think of anions, those are negative ions, they're always larger than the parent atom. So then we'll talk about chlorine, plain Cl, versus chlorine minus Cl that's gained an electron. The anion, chlorine minus, is larger than the parent atom, just plain chlorine. That's because when adding electrons, the number of electrons repelling each other increases, but the protons do not. Electrons are gained. Protons are not. The protons aren't going to change. If it's chlorine, it's chlorine. It has 17 protons no matter what. No matter whatever happens to the electrons, the protons stay the same. So the electrons are gained, but the protons are not. This causes the electrons to move further away from the nucleus. Additionally, there are more electrons than protons in these items, and therefore the force of attraction on each electron is reduced, and additional forces of repulsion between electrons are created. In some instances, the radius nearly doubles when electrons are added. So electrons are gained, protons are not. Each electron experiences less pull from the protons because now we have more electrons and the same number of protons. So then a smaller effective nuclear charge. Okay, so next we've got activity or reactivity. Metals tend to lose electrons. Pretty much everything on the left-hand side of the periodic table will lose electrons. So the most active metal is in the lower left-hand corner. Again, a little periodic table. The most active metal, if we think of the metals over here on the left, is, say, francium or cesium or barium. And that is because the atoms are much, much larger in that corner of the periodic table. So less energy is required to remove an electron. So it's easier to remove an electron, and it reacts quicker. Whether electrons are gained or lost, when electrons change, that's when a chemical reaction takes place. So in this case, it takes less energy to lose one, so not very much energy to have a reaction. For nonmetals, these are in the upper right-hand side of the periodic table. The most active nonmetal is in the upper right-hand corner. First of all, completely ignoring the noble gases because they're virtually inert anyway. So we're talking about fluorine, chlorine, oxygen. The most active nonmetals are in the upper right-hand corner because the atomic radius is smaller. So gained electrons will have a greater effective nuclear charge and will be easier to gain. The atoms are smaller due to a greater effective nuclear charge. Gained electrons will be added closer to the nucleus, and so electrons will be added more quickly. So whether electrons are added more quickly for the nonmetals or electrons are removed more slowly for the metals, whenever electrons change, that's when a chemical reaction takes place. We have electron affinity. That's the energy change associated with the addition of one electron to an atom rather than the removal of an electron, which is ionization energy. Across a period, the electron affinity increases because atoms are smaller. Due to a greater effective nuclear charge, and gained electrons will be added closer to the nucleus. As you go down a group, the electron affinity decreases because the atoms are larger. Due to a greater number of energy levels. And gained electrons would be added farther from the nucleus. So it's not as attractive to gain an electron for a larger atom than it is to gain an electron for a smaller atom. And our last trend is electronegativity. It's the ability of an atom and a molecule to attract shared electrons to it, a measure of the attraction of an atom for electrons in a covalent bond. Noble gases do not tend to form chemical bonds, therefore they do not have electronegativity values. So if you're thinking about your miniature periodic table, we're going to, again, completely ignore the noble gases as if they're not there. So the electronegativity trend, as you go across a period, electronegativity increases because the atoms are smaller. Due to a greater effective nuclear charge. And gained electrons will be added closer to the nucleus, therefore there's a greater attraction for electrons. So then as you go down a group, the electronegativity decreases because the atoms are larger. Due to increased energy levels. Gained electrons would be added further from the nucleus, and therefore there's a smaller attraction for the electrons. Last thing before we go, let's kind of fill in this periodic table, maybe on that blank page that you had your periodic table written on, to show where the trends are going. So, as you go across from left to right, size decreases, electronegativity, En, increases, effective nuclear charge, assuming you're not changing groups, just going straight across, increases, electron affinity, Ea, increases, and activity within the nonmetals only increases. And I think that's all for going across. As you go down, size increases, electronegativity decreases, the number of energy levels increases, the electron affinity decreases, and the activity for metals only, not for nonmetals, will increase. And then as you go up, you should be seeing electronegativity increase and size decrease, pretty much the opposite of the metal corner, the blue arrow in the bottom. The activity for metals only will increase. If you're going up on, for non-metals only will increase. If you're going up on the metal side, the activity will decrease. So sodium will react much less violently with water than francium will. And the effective nuclear charge will increase because the electrons are much, much closer to the nucleus. Okay, well, there's periodicity. I hope you enjoyed our unit on atomic theory, and we'll see you next time.